Welcome to The Explainer. Today, we are diving into a fundamental component that is, honestly, the unsung hero of precision electronics. It's all about one thing: creating a perfect, unwavering flow of electricity. Let's talk about the current source. So let's set the scene. Imagine you're designing a really high-end audio amplifier or maybe a critical medical device. Your design is brilliant, but it's also incredibly sensitive. Any tiny little fluctuation in voltage from somewhere else in the system could throw the whole thing off. So what do? How do you guarantee a perfectly constant, stable flow of electricity no matter what else is going on? Well, that exact problem is where the current source becomes our hero. So what exactly is this thing, and how does it pull off this magic trick of constant flow? At its heart, a current source is designed to be, well, stubborn. Its one and only job is to deliver a very precise amount of current. The voltage can spike, it can dip, it can do whatever it wants, but that flow of electrons, it stays completely locked in. To make this super intuitive, let's use the classic water hose analogy. Think of voltage as the water pressure inside the pipe. It's the force that's pushing everything along. Current, though, that's the actual flow. It's how much water is actually coming out of the nozzle every second. A current source is like a magical nozzle that makes sure the exact same amount of water flows out, whether the pressure behind it is a trickle or a blast. And this brings us to a really cool, kind of beautiful concept in electronics called duality. See, a current source isn't just some other component. It's the conceptual opposite, like a perfect mirror image of a voltage source. Think of them as two sides of the very same coin. And you know what? Understanding this duality is the key to really mastering both of them. But as with pretty much everything in engineering, there's the perfect world we see in textbooks, and then there's the messy reality of what we can actually build. This distinction is absolutely crucial. So let's break down the difference between ideal and real current sources. First up, we have the ideal current source. This is the one you'll find on paper, a perfect theoretical concept. Its symbol is super simple, just a circle with an arrow inside, representing a totally flawless, unwavering current. So what makes it ideal? Well, it's literally perfect. It delivers a perfectly constant current, it's completely independent of whatever voltage is thrown at it, and this is the most important part, it has an infinite internal resistance. That infinite resistance is the theoretical secret sauce that lets it completely ignore the outside world and just do its one job perfectly. Of course, we can't actually build things with infinity, so we have to move from theory to practice. In the real world, we create what are called practical current sources, and we usually build them using components like transistors. And you can see the difference right there in the circuit symbol. The practical, real-world model adds a resistor in parallel with that ideal source. And that resistor is everything. It represents the real-world imperfection, its internal resistance that we just can't escape. And that's really the key. A well-designed practical current source has an extremely high internal resistance. We're talking megaohms, which is huge, but it's never infinite. And that means a tiny, tiny little bit of its current might be affected by the rest of the circuit, making it just a hair less than perfect. Okay, so now that we get the whole ideal versus real thing, let's bring back that idea of duality. By putting the current source right next to the voltage source, we can see just how perfectly opposite these two things really are. Just as a quick reminder, a voltage source, like a battery, its whole job is to provide a constant voltage, and its symbol has the plus and minus signs. A current source, on the other hand, its job is to provide a constant current, and its symbol has that arrow showing the direction of flow. Different goals, different symbols. And right here, this is where their opposition becomes crystal clear. For an ideal voltage source to maintain its voltage perfectly, it needs zero internal resistance, absolutely nothing getting in the way. But for an ideal current source to maintain its flow, it needs the exact opposite, infinite internal resistance, to make sure no current can leak away or get diverted. They are fundamentally, by design, polar opposites. This fundamental opposition even changes the basic rules for how you combine them in a circuit. You can stack two batteries, two voltage sources in series, and you'll double the voltage. Simple. But try that with current sources? You get nothing. Instead, you have to put them in parallel to add their currents together. They play by completely different rulebooks, which is something every circuit designer has to know like the back of their hand. Okay, so that's the theory. But why does any of this really matter? Why would we go to all the trouble of building these specialized things? Let's take a look at where current sources are the hidden workhorses of all the tech we use today. The truth is, they're everywhere in modern electronics. In an amplifier, they provide that stable foundation that lets a transistor boost a signal cleanly, without distortion. In a timer circuit, they charge a capacitor at a perfectly steady linear rate, which creates a super reliable clock pulse. And inside the microchips that power, well, everything, they act as smart, efficient components that save a ton of power and boost performance. And ultimately, that's their superpower. Current sources provide the rock-solid stability and predictability that high-performance electronics absolutely demand. They're like the silent guardians inside the circuit, making sure every signal is clean and every component behaves exactly the way it's supposed to. So once you really get the difference between forcing a constant voltage versus forcing a constant current, it kind of changes how you see all electronics. With that in mind, I'll leave you with this thought. From the LEDs that light up your screen to the charger that's powering your phone right now, where else in the tech you use every single day do you think a constant, unwavering current is the secret ingredient?
Thanks for watching.